Hi everyone, this is the first video from section 14.6 and we'll focus on the topic of directional derivatives. So here we see a weather map which shows a contour map of the temperature function T for the states of California and Nevada at 3 p.m. on a day in October. Now, the partial derivative of t with respect to x at a location such as Reno is going to give us the rate of change of the temperature with respect to distance if we travel east from Reno, right? That partial derivative with respect to x is going to give us the rate of change if we travel in the direction of the x-axis. And similarly, if we take the partial derivative with respect to y, that will give us the rate of change of the temperature if we travel north, if we travel in the direction of the y-axis. But there are a lot of other directions we may want to travel in, right? What if we want to know the rate of change of the temperature if we travel southeast or in some other direction besides just the x-axis or the y-axis? So here's an example. Let's estimate the value of the directional derivative of the temperature function at Reno in the southeasterly direction. So since we're given a contour map to work with, we're going to find a point which is northwest of Reno with the temperature of approximately 50 degrees and a point southeast of Reno with a temperature of approximately 60 degrees. We can then use our key to compute that the distance between these 2 points is approximately 75 miles. And therefore, we determine that the rate of change of the temperature in this southeasterly direction will be approximately the difference, 60 minus 50, divided by the distance of 75. And so we get a rate of change of approximately 0.13 degrees Fahrenheit per mile traveled. Okay, now recall that for a function, z equals f of xy, the formal definition for the partial derivative of f with respect to x at the point x naught, y naught is this limit that we see here. Recall the derivative part is taking place with respect to the x coordinate, and that y coordinate is just being left alone, being left constant. And this, recall, gives the rate of change of our function in the x direction or in the direction of the unit vector I, right? I is the unit vector that points in the direction of the x-axis. Similarly, here is our formal definition for the partial derivative of f with respect to y, where the derivative is taking place with respect to our y variable and the x variable is being held constant. And this gives us the rate of change of our function in the y direction or in the direction of the unit vector j, since j is the unit vector that points in the direction of the y-axis. Okay, but the point, remember, of this section is, what if we don't want to travel in the direction of the x-axis or the y-axis? What if we want to travel in the direction of another vector? So the directional derivative of a function f at the point x naught, y naught in the direction of a unit vector u with coordinates a, b is given by the limit that we see here. The limit as h approaches 0 of f of x naught plus ha, y naught plus hb minus f of x naught, y naught over h. Notice there's a derivative taking place in both components, the x and the y, with respect to the vector u, right? With respect to the components of u, the a and the b. Now, before we move further, it's always nice to just double check that a new definition lines up well with an old definition. So what happens if u is our old unit vector I, our vector pointing in the direction of the x-axis? So if in our formula we replace a with the number 1 and b with the number 0, we get this. So we've replaced a with the number 1, b with the number 0, and sure enough, what we have recovered is our formal definition for the partial derivative of f with respect to x. And that's exactly what we should get, right? If we're going to travel in the direction of the x-axis, we should be getting our partial derivative with respect to x. Similarly, if you replace the vector u with j, then you will see that you recover the partial derivative of f with respect to y. Okay, so here's our formal definition for our directional derivative. The derivative of a function in the direction of a generic unit vector u. Luckily, there's a nice formula to help us compute a directional derivative. It's this theorem here, which says that if f is a differentiable function of x and y, then f has a directional derivative in the direction of any unit vector u with components a, b. And the directional derivative of f with respect to u is found by taking the partial derivative of f with respect to x and multiplying by a, plus the partial derivative of f with respect to y and multiplying by b. Before we do an example, I do want to make one quick remark. Note that the definition is given for a unit vector u. So when we're talking about directional derivatives, we always want to make sure that we're moving in the direction of a unit vector. All right, let's do an example. Let's find the directional derivative of the function x to the 4th minus x squared y cubed at the point 2, 1 in the direction of the vector v given by I plus 3j. All right, well remember I just said that when we're talking about directional derivatives, we must be moving in the direction of a unit vector. But the vector v that we've been given here is not a unit vector. If we compute its length, we see that the length of v is the square root of 1 squared plus 3 squared, so the square root of 10. And therefore, we're going to need a unit vector that points in the same direction as v. So a unit vector in the same direction as v is the vector which I'll call u. We're going to take the vector v and divide by its length. So we get the vector 1 over the square root of 10, 3 over the square root of 10. And now we have a unit vector pointing in the direction we want to travel in. All right, we're ready for our directional derivative. Here is our formula. So we start with the partial derivative of f with respect to x. That is 4x cubed minus 2xy cubed times a, the x component of our unit vector, which is 1 over the square root of 10, plus the partial derivative of f with respect to y, which is minus 3x squared y squared, times the y component of our unit vector u, which is 3 over the square root of 10. So this gives us the directional derivative of f in the direction of the unit vector u at any point xy. We're asked to find the directional derivative at the point 2, 1. So our last step is simply to evaluate at the point 2, 1. So doing so, we're left with negative 8 over the square root of 10. So that would be our directional derivative, our rate of change of the function f at the point 2, 1, moving in the direction of the vector v, I plus 3j. All right, so that's all for this introductory video to directional derivatives. In part 2, we will be looking at something called the gradient vector. And the gradient vector is going to help us answer the question, which direction should we move in from a given point in order to maximize that directional derivative? But more on that later. We'll see you there.